Alright, welcome everyone to the second video on chemical thermodynamics. In this video, we're going to talk about just what are the laws of thermodynamics, specifically the three laws. There's some people that say there's like a zeroth law or blah, 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 but like these are the three kind of original fundamental laws of thermodynamics. Okay. First law of thermodynamics, energy can't be created or destroyed. Okay, the energy of the universe is constant, right? That's just the first law of thermodynamics. We won't really go too much more into it than that. Just, energies can't be created or destroyed. Right? The second law of thermodynamics we've actually already talked about in the first video. The second law of thermodynamics states that any spontaneous process, there's always an increase in the entropy change of the universe. Okay? Right? So that means, right, if the entropy change in the universe is greater than zero, that process is spontaneous. Right? So we've talked about that in the previous video. And then the third law of thermodynamics just says that the entropy of a pure crystal at absolute zero is zero. So the third law of thermodynamics is basically saying, hey, zero entropy is for a perfect crystal at 0 Kelvin. Okay, right? It's sort of defining what is the minimum entropy one can have, and it's zero. Right? There's no such thing as a negative entropy for a substance. Right? You can have a negative change in entropy. Right? Your entropy can decrease, but your entropy can never go below zero, where zero is the minimum, and that's a perfect crystal at 0 Kelvin. Okay, but focusing on the second law of thermodynamics, right? Again, it's saying entropy change in the universe, right? That is telling me about whether or not something is spontaneous, right? If this is greater than zero, then that is a spontaneous process, right? Well, entropy change in the universe is just the entropy change in the system plus that in the surroundings, right? But really, what we care about is the system, right? When we're measuring things in the lab, right, doing things in the lab, we care about like our system, our reaction, right, our beaker, right, thing we're focused in on. That's what we care about. We don't really care and want to try to measure and predict, right, what's happening in the surroundings at all times, right? It's kind of annoying, it's tedious, it can be difficult, right? So we really like to get rid of this system part, okay, right? And because we don't want to have to measure everything in the surroundings, right? Because the surroundings is a lot, right? It's everything else in the universe but the system, right? But the thing you care about, okay? And so we would love to kind of get at this thing where entropy of the universe tells us of whether or not something is spontaneous. We'd love to be able to try to get that understanding of whether or not a reaction is spontaneous by measuring something just in the system, okay? Right? We really don't want to have to calculate the entropy change in the universe. We want to get just something in the system in order to predict spontaneity, right? So again, the second law of thermodynamics tells us that the entropy change in the universe, right, is greater than zero for a spontaneous process, right? But we would love to be able to measure just stuff in our system, right? Because again, the universe is the system plus surroundings. We don't have to measure the surroundings, right? And so the question is there some way we can predict whether or not something is spontaneous by just focusing in on the system, okay? And that's what the next video is going to be all about.